just to just see where any issues might arise. So one of the problems that I've given you is that these two chemicals have been mixed up, which is not an original thing that's happened. But the maximum UV absorption for one is at a certain wavelength, a high energy wavelength, and the other is a lower energy absorption. So the question is, which on earth is which? So I'm going to try and draw. I'm not sure how well I'm going to draw, so just bear with me. Let's see if we can't try and get started at least on this problem. So let's go to a region over here, and so let's maybe try and define what problems we have. And so what we've got on the one hand is we have got this compound here, and on the other hand we've got this compound, Now, what do we know about them? Well, we know that the length of a pi system is about L, and the length of its pi system, the pi will be p orbitals in line all the way through, so the length of this pi system is about 3L. What else do we know? Well, in this one, there are only 2 pi electrons, so when we try and draw the energy levels, we've got energy level 1 and energy level number 2. So there's 1 and 2. And on this side, we've got 4 pi electrons. So we've got energy levels 1, 2, 3. And we've got these are full. And so the maximum absorption will go from 1 to 2 in this case. The maximum absorption will go from 2 to 3 in that case. And the question then is, which one is going to absorb at 192 and which one is going to absorb at 243 nanometers? So the question is which is going to absorb at which. And all we need to be able to solve this is we need to know that En is equal to h squared n squared over 8ml squared. So for the first case, for the 1 to 2, we're going to have to calculate, put a 1 in here, and then we're going to have to put a 2 in here, and we're going to then have to subtract them to get the difference. And of course, for the other case, we're going to have to put a 2 and a 3 here, and we're going to have to subtract them to get the difference. So for the first case, so let's do star and star star. So for the first case, the change in energy is going to be the difference between the two. So we're going to have h squared over 8ml squared all into the higher energy. So we'll calculate it for 2 squared, which is 4. And we'll calculate again for 1 squared, which is 1. So the change in energy is that, which is going to be 3 times h squared over 8ml squared. Right, for the second case, the difference is between 2 and 3. And so your change in energy, your delta E, is going to be the same thing again, but now we've got an interesting case with h squared over 8m, but it is 3l squared, all times 5, and we're going to do 3 squared minus 2 squared, which is 3 squared is 9, So it's 9 minus 2 squared is 4. And I get that as being, it's going to be 5. But I'd also like to take this out, this 3 squared at the end, put that 5 over 9 down here. And I end up with h squared over 8ml squared. So I hope that you can see in this that this here is a greater energy. So when you've got 3 is greater than 5 over 9. So this is the greatest energy, that's a lower energy. The greatest energy is going to correspond to the shortest wavelength. And the lowest energy is going to correspond to the greatest wavelength. So we can now then decide which is which between the two. Okay. Please check my arithmetic and my algebra. Just check that I've got the right numbers, but this is as expected. As you get a longer wavelength, as you get a longer molecule, the absorption is, the jump is a lower energy. Okay, so that's the first question that I wanted you to explore. And there are a couple of others, so let's just go and have a look at, just hang on a moment. Let's see if that works. There we go. Okay, so there was another problem that I'd pasted on. Yes? Question? I'm struggling to hear. Just please speak loudly. Hello?
So do you mean that the higher the energy ratio, the lower the wavelength?
Yes. So, so what we have is that a higher energy means a greater frequency, which means a shorter wavelength. So long wavelengths are low in energy, and short wavelengths are high in energy. Does that make sense?
Yes, Prof. Thank you.
Perfect. Okay. Right. The second problem that I wanted to just see if there were problems with is rotational spectrum of carbon monoxide. Okay. So this is the rotational spectrum of carbon monoxide at 50 Kelvin. That's really, really at a very low temperature. And this here is the spectrum of carbon monoxide at a reasonable temperature. So the first question is why they're different. You'll notice that in this one I can see absorptions in wave numbers up to 100, whereas here I can't see those absorptions close to 100. The question is why are we seeing those bands close to 100 when you're at a high temperature, and while you're at a low temperature you don't see anything else? Any ideas? Anyone? Why would there be a difference in the at different temperatures? No one. Of course. Yes, yes.
Can I try answer?
Yes.
So I think it's because of the relationship between temperature and energy in the Boltzmann distribution equation.
Oh, fantastic. Yes, yes, absolutely. So that's fantastic. So yeah, if you at 298, then of course you've got a distribution, your energy levels get more populated, and you can calculate from the difference in energy what the relative populations are. But of course remember as well that there is some degeneracy. Please have a look at the slides. There's some degeneracy in the rotational energy levels, which means that you've got fewer, so at your lowest energy level, there are fewer possibilities, and so the distribution is a slightly modified Boltzmann distribution. And so, yes, if you want to see this absorption here, you've got to make sure that you start off with some molecules with the energy that corresponds to the low energy for that absorption. And of course, at low temperature, there are no molecules with that energy, so there's no way you're going to see that absorption. So you do need a distribution of energies to be able to see these absorptions at higher wave numbers. So, but that doesn't really interfere with the problem at hand. And the problem is really about looking at the bands on the spectrum and calculating the moment of inertia and the bond length of those two. And so those are quite straightforward to do. So maybe I won't go in depth in the solution, but maybe we can just get started on that and just see where we're at. Okay, so let's go back to my so let's just try. Okay, so right, so let's have a look and see. So what we've got in this problem is that the separation of the bands. And so remember that 2b. Just hang on. Yeah, there we go. Okay, right. So 2b is, and you can calculate the difference quite easily. The difference in that, just hang on. I've lost my settings. Apologies, my window has died on my other system, my reference system. So apologies. I'm going to need to look for just okay. My window died on my other screen, so I don't have the numbers in front of it. Didn't have the numbers in front of me, but I can get them now, and it is 3.86 centimeters to the -1, and it's quite nice because if you choose any two of those numbers, there are three numbers given to you, there are three bands given to you, and those are 30.88, 34.74, and 38.60. You pick any pair of those, and we get the difference is 3.86 per centimeter to the -1, which means that you can then calculate the rotational constant as being half that, and don't forget to convert it to meters to -1, and so you should get something of like 193 per meter to -1. And then from here, of course, then we've got to calculate what I is, and of course for I you're going to use and so we know that B is equal to H bar over 4 pi Ci, which means that you can rearrange, of course, to get your I is equal to H bar over 4 pi C. Okay, so that's relatively straightforward. Of course, to go anywhere, you're also going to have to calculate your reduced mass. And of course, your reduced mass in this case, given your exact values, you've got 1 over exactly 12 by definition, plus that's carbon 12, plus 1 over the oxygen is 15.9949. So that's 1 over mu, sorry. And so you'll be able to get your mu easily out of that. But when you follow this calculation through, at the end of your calculation, you'll also use I is equal to mu r squared, and out of it you will get, from that you will calculate your R. Okay, but then question 3 works backwards. So for question 3, once you have your R, you're going to then work backwards. For question 3, you've got a different mu. So you'll be able to find your different reduced mass is different, but your R is the same. It's chemically the same compound, which means that if you've got mu and R, then you can calculate I, because I is equal to mu R squared. And if you know what I is, you can calculate what B is using the H bar over 4 pi Ci, which means that you can calculate what your 2B, your expected 2B is. And so you can predict for the different isotope what 2B is going to be in the spectrum. Okay, so when you've got carbon 13 instead of carbon 12, what on earth is going to be the separation in the spectrum? Okay. Any questions with that? How to proceed with that? Okay, now we've got a really interesting, I find part, this is straightforward because we've been through this kind of problem in lectures, but I really find the next problem quite interesting because it shows really the problems that you might encounter with some of the things. So this is HCl, and this here is what your rotational spectrum, your rotational vibrational spectrum of HCl looks like. And so the first issue that we come to is why do we see these doubling up of these bands? Why do we see a smaller at about a third of intensity, a smaller set of bands at about a third of intensity, and these larger set of bands at about 2/3 of intensity? The question is, why would we see that? Any ideas? Anyone?
Maybe the isotopes of chlorine that have different masses.
Absolutely. So the thing is, the isotopes of chlorine are really an issue because of course, if you've got a slightly different mass of chlorine, so if you've got chlorine 37, then of course your moment of inertia is going to be different. Its reduced mass is different. Its bond length will be the same, but its reduced mass will be different. So I is equal to mu R squared will be totally different for it, which means that your rotational energy levels are different, and so your bands are going to appear in a slightly different place to that of chlorine 35. And so we get the ratio of these isotopes. And of course, in this problem, we are only interested in the chlorine 35. We're going to look at the chlorine 35. But remember that chlorine is a mixture of isotopes. And so we'll have chlorine 37 available as well. There's another problem that we have in the spectrum, and that we see the P branch on the left. And remember, the P branch is where you jump up a vibrational level, but of course you go down a rotational level. And the R branch is when you go up a vibrational, but you go up a rotational level. But the place where you don't change rotational level, the Q branch, is forbidden in this case. So we don't see anything happening there. And so if we want to look at the vibration of HCl, we're in trouble. And of course, looking at the fundamental vibration of HCl is really important because from that vibration, from the fundamental vibration, you can get the force constant for a bond. So if I can translate all of that to energy diagrams, so you can see this here is our first vibrational level. That's our second vibrational level. And if you look at these blue lines that are sitting there, you'll see that they're jumping rotational levels. So this starts at rotational energy level number 1, ends up rotational energy level number 0. So the rotation's changing here. Here's going from 2 to 1. The rotation's changing. Here, again, the rotations are changing. And that's not what we want when we're looking at vibrational spectroscopy. We want just vibration to change. But it's not there on the spectrum, so we can't have it. So our problem is that we want to know what the distance is, or maybe in distance in terms of wave numbers or energy, between the jump between level 0 here for rotation to level 0 for rotation. This jump is only a vibration. So that, if we knew that fundamental vibration, we'd be able to get the force constant for the bond. And so that's what we need. But what is quite nice about this is if you have a look at this line over here, this at wave number 2864.8, and this blue line at 2906.0, you can see that this jump for the vibration alone is a little bit greater than this one and a little bit less than that one. So if we make a very bold assumption and say that these energy levels are all the same, we would be able to make the jump and say that this here is the average of these two. So this line here is the average of a slightly longer line and the slightly shorter line. And that average line, you can see nothing changes with rotation. This is all about vibration. And so we're firmly, once we're firmly back into pure vibrational spectroscopy, in which case we can use everything that we have available to us to calculate the force constant. Okay, so the way you deal with that problem is quite interesting. Just hang a moment. I'm trying to stop. Go back to my page. Right. So so if we can just got my reference on the side. So what we've got is those two central bands. So we've got the two central bands are 2864. Sorry, 286. Let's just undo it. And so I'm going to try and write it more clearly. 2864.8 centimeters per 1 minus 1. And that jump really is the one that goes down in rotation number. And then the other one is 2906.0. And of course, the average of those is going to be, so the average is going to give us our fundamental vibration. And so we can get that in terms of, remember that you're going to have to put it in terms of meters. So, so you should get something like, it should be quite a large number. So something like 288,540 a meter to the minus 1. So it's a really large number. And then of course, don't forget that you've got now this equation that's available to you is 1 over 2 pi c, 1 over 2 pi c into the square root of k over the reduced mass. And of course, we've got mu naught for HCl with 35 Cl, chlorine 35. We know everything there is. We know pi, we know the speed of light. We've got everything, and so therefore we can find K from this. So that's really nice in terms of it pulling out the fundamental vibration, we can extrapolate and decide what the fundamental vibration is going to be. And if we know what the fundamental vibration is going to be, we're going to be able to calculate the force constant for the HCl bond. Okay. Any questions? Right, the final part of it, final part of that question is, it says, well, here's an interesting one before the final. Maybe I can throw this in your court. Why are the rotational constants in the upper and the lower levels not precisely the same? So what I'm saying now is, if you look carefully and have a look at this jump here, over here, it's not the same as this jump over here. And going from level 1 to 2 is not exactly the same as going level to 1 to 2 up there. Why might these lines be slightly different in spacing between these lines in terms of energy, rotational energy levels? Any ideas? Anything? Why would your rotational energy levels be slightly different when you go up to a higher vibrational energy level? It's really important. Okay, so think about it. If your molecule has a great degree of vibration, what do you think? Do you think that your molecule will be as compact, for example, if it's vibrating at a higher energy level? At a higher energy level, your molecule isn't going to be quite as compact as it was before at lower energy levels. And that's going to affect the rotational energy levels. You can imagine what your average from your center of mass is going to be. So you are going to affect your rotational energy levels. So just be careful of it. So think about that. See if you can get in your mind why the rotation energy levels are going to be different. Okay, and think in terms of the moment of inertia. For calculating the bond length for 1H35 in the ground state is quite nice. What we need is we need two lines that are at the same place at the top, because we're not interested in these upper energy levels. We're interested in a change in the bottom. We need two blue lines that are at the same time at the top. So two energy jumps that go from the same place. And I see that there's this 2843.3 starts at energy level number 1 or ends there, and 2906.0 also starts from the same place or ends in the same place. So they're exactly the same at the upper vibrational energy level, exactly the same. The only difference is in the lower energy vibrational level. And you can see that the one drops down to energy level number 0 and the one drops down to energy level number 2. But if we can see our spacing, our grid spacing there are three spacings there. There are three of the 2B spacings, 2 HCV spacings, different between them. So if we take the difference between the 2843 and the 2906, the difference is going to be 6B. And if the difference is 6B, then we can easily calculate what B is. And if we know what B is, then we can calculate what I is. If we know what I is, we can calculate what the bond length is. So maybe if I can summarize that as to what where we're going with that is, so if I can just summarize in terms of what's happening. So what we have is we've got 2843.3, and we've got the other one which is 2906. 106.0, and the difference is between J is equal to 0 and J is equal to 2 in the lower vibrational energy level. And so what we're going to be looking at is the ground state bond length is what we're looking for. And so the difference is that, and that is in wave numbers. So we find that, so the difference between J is 0 and J is 2 corresponds to 6 HCV. So therefore 6B is the difference. And so therefore you will be able to find that what B is. And just to check that you're on the right track, just check that you get B to being something like 1045. And show you're working. Just check that you've got your working and your conversion to meters, etc., all sorted out. Then of course everything works out well from this point because you've got this equation, B is equal to H bar over 4 pi C I, which means you can get I, and then you've got to calculate the reduced mass for 1H35 Cl, and then of course use I is equal to nu, I is equal to nu R squared, means that we can calculate R. Okay, so those are two very useful problems. Please attempt them and make sure that you upload your solutions to Are You Connected. Okay, I am working my way through marking stuff in Are You Connected, so you can see that I've completed marking from the first week. I'm busy working my way through marking for the second week. So just check when it's completely marked where your errors are. If you're worried with how it is, you can always reattempt and email to tell me you've reattempted it, or you can ask me for hints as to what might have gone wrong in your attempts. So the marking will be done. And if you've got any other queries about the QM section of the course, please feel free to contact me. Okay, any last comments or queries before we sign off on the QM course? Okay, well, if there are no questions or comments from the QM course, there's a question for the linear free energy course. How long are we going to run the course for? Just give me a moment and let me just see. I just need to get a document up for us. Just give me a moment. So if I can just show you where we're at. So over here, so let's see where we are. We're on the 25th of May now, and we have completed the QM modeling course. The linear free energy course then runs through, I think, to about Wednesday. So to Wednesday the 3rd of June. So it's about a week's course, and it's a very different set of work to what we had before. Okay, Any other comments, queries? Okay, then I'm going to sign off for QM and we'll start on linear free energy tomorrow.